you do take your attendance in the spectrum. All right, and next is I will recap, what we have done so far from the last chapter or last lecture. Okay, so far we have done the sources of error. Okay, in the first week we already learned about approximation error, true error, okay, relative, absolute error, and so on. And then the last lectures we will cover about the truncation error, as well as we covered that the round-off error, okay, and then also we discuss about data propagation error, okay. So we already covered the most of the part of the errors, okay. And this week we will cover the data representations. Okay, so mostly we will cover today is how the computers make that calculations in the numerical methods. Okay, so the way you do and the computer different. Okay, the computers or machines is do in a different way, and there is a lot of that arithmetic you have to consider when you come to the conclusion or when you come to the calculations. Okay, so please be aware that when this unit is more focusing on that the approximation solution, so your significant and decimal numbers is a one of that importance, and you have to give a great importance for that. Okay, now, so before I start today lecture, do you have any questions? Okay, if any question, you can leave in the chat box. Okay, all right. Representation of the data. Okay, in mathematical method, okay, data is a one of that very important, and you may know how to represent your data in that mathematical terms. Okay, especially when we use arithmetic calculation by using a computer, so we have to consider the approximation, which means we have to look into that the decimal numbers as well as the significant figures. Okay, so this is what we're going to discuss today. Here we go. So the content of today's topics will be on decimal places, significant figures. Check laser highlight. Okay. Okay, significant figures, and then we will discuss about the computer arithmetic or machine arithmetic, and then the topic contains a normalized decimal floating point, and then overflow and underflow error. Okay. Okay, we're expecting the end of this chapter, so you'll be able to determine the decimal places. You know how to identify the significant figures, and then you also learn how to calculate by the computer does the calculation by using that arithmetic, and then you'll be able to write a normalized decimal floating point, and also you know how to calculate overflow and underflow of error for the particular solutions. So this is what the topic will be covered today. Okay. All right. What does it mean the decimal places? Okay, as you know, all the digit numbers is after decimal points on the right hand side. If you see that any of our numbers, if there is any like a dot point and followed by the any numbers, and we called as a decimal numbers or decimal places. Okay, decimal numbers. As you can see some example over here. All right, so the number is a given is here is the first row is a 14. Okay, since there is a no any decimal point there, all right, so that means we can claim that there is a no decimal places, or we can say that simply as 0 decimal places. If it is the 2 decimal places, okay, if we see the 0.25, so if you can see, obviously there is a 2 decimal numbers after that dot point, so we can claim that the number has 2 decimal places. Okay, now look at that, the example 3, 0.059700. Okay, as I said earlier, whatever number come after that any dot point, we calculate it as a decimal number. So decimal numbers here for this case, 1, 2, 3, 4, 5, 6. So if it is the 20 given even after that the non-zero value here, so we must also be calculated. Okay, if it is not, then you just leave it that at the last number. If it is 0, then given, so you have to calculate itself. Okay, so how many decimal places there? So there is a 6 decimal places in this number. Okay, now look at this. It's a 10000. Okay, so how many decimal numbers contain this figure? There is a no decimal number appeared on the number, so you can say that it's a 0 decimal numbers. Just simple as it. Likewise, the others. Okay, so this is a 6 decimal places. Okay, this as well as 6 decimal places, and this as well as that the 7 decimal places right after that dot. Okay, so this is how you need to determine that decimal places. Okay, all right. Now come to that the significant figure. Okay, is a vary from the decimal numbers. Significant figures, we only consider the starting with that the first non-zero digit until the last non-zero digit or 0 decimal. So it's called as a significant figure. Okay, so take a look at this example. Okay, this they given the same number, the same figures, the one I given in the example, previous example. Okay, now take a look. This is a 14. So 14, as we know, just now we had a 0 decimal places, right? 0 decimal place. So for this case, is a significant digit. So how many significant digit the number has? So there is a 1, 2. So we have a 2 significant digit. Okay, move on to that, the second one, 0.25. Okay, so as we know, the significant must be first non-zero digit. So this should not be calculated even there, even right after the 0. So since the first number right after the 0 is a 2, so we count that, so which means 1 and 2. So the number 0.25 as 2 significant digit. Okay, look at that the example 3, 0.059705. Okay, so now, as I said earlier, based on that the criteria, the number non-zero figure will be counted. So which means for this case 0.059700, since the 0 is start after that dot point, it will not be counted. So we just start from 5. So 1, 2, 3, 4, 5. So we have a 5 significant digit in these numbers. Okay, all right, now look at this. It's a 10000. It's a 10,000. Okay, so this figure has the 1 significant digit. So because the right after that 1, we all got 0, so it will not be counted. So this figure has a 1 significant figure or significant digit. Now look at this. 100.0000 and 00. So there is a how many significant figure as? So since there is a dot here, so it has to be counted. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So which means there is a 9 significant digit. Okay. So likewise, the same things goes to here, 5.000001. So it has 7 significant digit, which means you need to count from the first digit, which is 5, and until the last digit. Okay, now take a look. This example is a 0.000009. Okay, so this is there is a numbers is a start from 0, and the first digit is start for non-zero value is at the point here, which is 9. So it's just only 9 in there, so we count as one significant digit. Okay, so now this how that is a differ from that decimal numbers to significant figures. Okay, so decimal numbers and how to determine that the significant figure or significant digit. Okay, is there any question, guys, from here? Any question? Is it clear?
Clear.
Okay. Now we look into that the decimal places versus significant figure. Okay, what the difference between the decimal places and the significant figure? Okay, take a look on this example. Okay, all right. So decimal places is a more focus on the precision. Okay, so precision of the numerical value. Okay, it's not talk about accuracy. Yeah, remember, decimal places is more look into precision. Okay, but the significant figure is important in order to determine the accuracy. So the accuracy is come from that significant digit or the significant figure. Okay, take a look this the diagram. Okay, so we call that the first diagram here. Just okay, the first diagram here. This is indicate as that the high accuracy and high precision because the focal point is at the center. All the marks or the target is ended up in that center point. So that means we call this is a high accuracy and high precision, and all the target is come closer to one to another, and it's focused on the center point. Okay, so this is called a high accuracy and high precision. Okay, look at this diagram. This is called a low accuracy and high precision because you know why? The accuracy is not here at not the center point, but this is the high precision because all that the target is towards in that the same region. So this point. So that means we call is a high precision, but however, this is low accuracy because it just out of the center part. Okay, now high accuracy and low precision. Okay, as you can see that all that the target point is appeared in the center. Okay, however, it's called as a low precision because all the target is hit just right bit a distance from that or away from that the one to another. So this called is a low precision. Okay, and now look at this. This is represent for the low accuracy and low precision because all the target is all around the one to another, as well as it's out of the target point. Even sometimes here or here target is also we call as a low precision or low accuracy. Okay. All right. Now we move to the next subtopic, which is complete arithmetic. This is involve a lot of calculations. All right. So this is like very important for you in order to calculate that how the computer do a calculation. Okay. So you also will be assessed based on this. Okay. So usually you know how to understand how the computer or machine will be do arithmetic operations. Okay, this is what you're going to do in your exam as well. So you need to, in practice, you're going to attempt how you're going to calculate as how the computer does. Now, computer arithmetic usually is a arithmetic operation is carried out by the computer or machines. So usually machine, we call machine any machines. Okay, computers we represent to. Okay, the calculation include the arithmetic system of is can be integer or fixed point, and as well as the most important we call as floating point. So in this topic, we're going to discuss more on the floating point, how the floating point is works, right? And how we get the solutions. Okay. So in C++, usually by practice in C++, please be aware that the float data as a 7-digit. Okay, the float data. So remember when you just write a programs, okay, when you write a program, so usually you could see that, you know, like C++, right? So you just write a float area, right? Okay, so usually it will be the data will be only that 4-digit figures. Okay, so if you integer, okay, that is usually integer, float, double. Be familiar with those kind of these guys, because you're going to do later in the C programming when in the structured programming. Okay, so long double. Okay, so this all you're going to do, you need to going to learn in that the structured program of C++. So remember that the float data usually will be 7-digit, double long float data will be 16 digit, and long double as a 19-digit. So this is a practice, is a usually we use in that the C++ in order to represent all the numbers, because say our calculation involve great numbers of figures, so then we have to use those command accordingly. Okay, so unless what happened, it will be the system will be stopped. Okay, or if it is this is what we call overflow, if the system will be stopped, otherwise it will be underflow, so all the digit will be reset to 0. Okay, so that means you will not get the accurate solutions. Okay, in computer arithmetic, so remember that there is a one terms we famous in use, which is we call as a normalized decimal floating point. Okay, in the short form we call as a NDFP. Okay, so which means the numbers, when we just store a numbers in that computer or in the machines, okay, and we process in the form of normalized decimal floating point. Okay, so take a look the example how we're going to write that the NDFP. Okay, see, look at this is a number. So this is a number, okay, and then this usual numbers is given, so 0.00000245993. So when we just convert the number into NDFP, so this has to be right in this form, which means this is we call 0.24593. We call this is a mantissa. Okay, usually they call as a mantissa. Okay. And yeah, okay, this called as a mantissa, and this is exponent, right? Or we call as an index. Okay, so what you need to do, you need to convert any numbers in this form. First you need to write in the form of this, in that NDFP form. Okay, so this number can be represented, so when you just move, so it's 1 2 3 4 5, so which means 0.2459993 times 10 power of minus 5. So this index represents that the number of your movement from that decimal places in order to be formed as a 0.2 something. Okay, now second one, likewise the same things. Now you need to form in the NDFP form. So you need to move in front. Okay. Is a become power 2. Okay, move in front. So this will be a, so it's a 0.2136569. So which means times 10 power of 2. Okay, and likewise this. Okay, so when you just move that the decimal into in front, so make it is a 0.96 something times 10 power of 7. So make sure this is, you need to write this first in order to do a calculation. Okay, so this is we call as a normalized decimal floating point. Okay, so remember that the x is a usually we represent that the plus minus. All right, this can be a number plus minus. So make sure 0 point any figures d1 is taken by usually 1 or 2, 3 or so on. So it's a non-zero value. Okay, okay, so when you just write in this form, guys, remember. And then the d2, d3, any numbers between 1 to 9. And then the n will be the index. Okay, n will be the index. Okay, so as I said earlier, so d1 this has non-zero value. Okay, so and then the di, okay, so the di is usually it will be given it should be di, okay, and then this n will be is any integers. Okay, represent any integers, and the d1 has to be between 1 and 9, and this here will be being just missed out. I will edit later, guys. Okay, it's a di actually. Okay, di and yeah, comma. Okay. So the n is will be the index. Okay, the n will be the index. Okay. Okay, mantissa, as I said earlier, so the mantissa will be the number in the form of the NDFP. Okay, so usually it will be between 0.1 to 1. So this will be the figures we call is a mantissa. Okay, so remember that the mantissa and the exponent, and okay, the exponent index times 10 power of n as a limited size in the computer. All right, because it depends on the computer that we use. Okay. Okay. Now we move on the k-digit decimal floating point form. Okay, the k-digit decimal floating form is can be denoted as the floating point. Okay, usually we just write in the FL. It stand for that floating point. The X is represent that the numbers, or that the figure number value numbers which is we're going to substitute. So first, all you need to do, you need to write in the mantissa forms. Okay, 10 power of n. So remember that the n is actually is the index or exponent. Okay, and then this the n is represent for the all between the n value fall between the m and m value, the small m and the capital M. What does it mean, the small m, the capital M? So this is represent that the boundaries. Okay, the boundaries depending on the computer. So which bit the computer or we using? Usually in IBM, so we have the certain figures is between the -77. Okay, to yeah, usually it's a -77 to yeah. around that figure. Okay, and depends on the question as well. All right, if the question wanted to calculate between the boundary, then you have to determine that the boundaries. But usually in the IBM, it will be given standard is between minus 77 to 78, I guess. Yeah. So you can check on the computers. Depend on the computers. Okay. If it is IEEE, set is a different. Okay. In the Intel, also you have to look into it based on the bit what they have. Okay. But just for that, your understanding is usually the question will be given. So this we call as a boundary. Okay. Okay, there are two ways to determine that the arithmetic operation, arithmetic system. We call as the decay. Okay, so decay is also we call as a decimal floating point. So one is we call as a round up number. Okay, so we call as a round up number. So the round up number is a decay which is represent for that decay, because when the computer calculate, okay, so it will calculate is not how we calculate in practice. Say for example, uh, Nor Azi, like she want to calculate 2.7. So when you round up the 2.7, what will be your answers, Azi? Nor Azi is here? Lim Jia Ki.
Yes, sir.
Okay, Lim Jia Ki. Okay, so when we just say you are going to round up that the 2.7, the nearest numbers, so what would be your answer?
Sorry, in how many decimal place?
No, if just like a one decimal numbers, you just round up 2.7 to nearest numbers, what would be that your figure
3.
will be? Okay, very good. All right, now say you're going to round up the 2.4. So what would be your nearest number will be?
2.
Okay, thank you very much. Okay, this how we're going to calculate by practice, but human, but the computer would not do that. Okay, remember, because it's just a machine. Okay, mostly the computer will be using that the chopping criteria. Okay, otherwise when we just root that round off number, so we have to declare in the system, in the usually in the programming we have to declare. So which means the decay, we have to declare that if between 0 to 4, so it will take the whatever number nearest to that the number. Okay, if it is more than 0.5, so more than 5 and above, so it will be calculate the nearest the other numbers close to the greater. Okay, but you see in computer what will do usually, if a 2.7 means the computer will read as a 2, even the 2.9 the computer will read as a 2. Okay, because this is like the system in the computer system or computer arithmetic, it will be set in that way. So because the computer has no memories to make the round up, so usually how we do, we write the programming in order to take the nearest numbers. Okay, okay, now so the round of numbers usually will be expressed in that two form, which is we split into the two category, which is so number whatever the point we number, you see, look at the 0 point, the decay, right? So this number is whatever fall between 0 to 4, and is the computer will be read up the nearest number below, and the number which is a greater than 5 and above to 9, so it will be read that the greater number closer to that point. Okay, the another way of the computer reading, computer system will read based on the chopping of numbers. Okay, we call it a chopping of numbers. So which means the decay is equal to it will read the decay value between 0 to 9. So whatever the number is fall between here, so it will be based on that these two numbers 0 to 9. Okay, so we don't the split in this form. So whatever the is comes like 2.9, this will be read as a 2. Okay, so we call as a chopping numbers or chopping of numbers. Okay, so let me take some example in order to see that some better understanding for the concept. Okay, so that you can get the clear picture. Okay, now take a look this example 1. Express that following numbers in the 4-digit decimal floating point form. Okay, so there is 3 question is there. Okay, you take a look at the first question. X equal to 0.32446 10 power of minus 3. So if you can see, this is already in the form of NDFP form. Okay, it's already in the NDFP form. Okay, now we're going to express the solution in the two form. One is the rounded form or rounded off form. Another is chopping of numbers. Okay. Now, if a round off numbers, as you can see that, so it's a 0.32 based on the 4-digit. Yeah, based on the 4-digit. The given number is x equal to 0.32446 10 power of minus 3. So if you can see that, since the question or the requirement is a 4-digit, so we just only consider 1, 2, 3, 4. Okay. So since this is a rounded, okay, we just have rounded up. So we have to look for the nearest. So you look at the digit after number 4. Okay, the fourth place. You look at the fifth place. Is a 6. It's a more than, okay, more than 4, which means it's 5 and above. So we just rounded to 5. So it's become 0.3245. Okay, but if you look at the chopping of number, if a chopping of number, what will happen is that doesn't matter if even is 6, you only counted as the number which is nearest low, which is 0.3244. So which means you get 0.3244 times 10 power of minus 3. Okay, so this is we call as a chopping of number. Okay, okay, now take a look at the second example. The second example is given as x equal to 0.0000459951. Say again, we only consider the 4-digit decimal floating point form. So the 4-digit floating point form will be, first what you need to do, you need to convert this, the original number, into the NDFP form. Okay, so you must change into the NDF form in order to write 0.4599951 10 power of minus what? 1, 2, 3, 4. Okay, minus 4, 10 power of minus 4. Okay, now then only we need to attempt that to round up of calculation, which is, if you can see, this is a 4-digit decimal point. So 4-digit decimal point is will be how many? It's a become 0.4600. If you can see the 4600, so it will be, look at this number, is a round up. Okay, rounded is to this is 5, you round, make the 0, and this become a 0, and you add on 1 here, is become a 6. So eventually what happened is it become 0.4600. So remember, it's when this nearest is 5, when you just you look for the nearest numbers. So since it's already like 5 and above, since we rounded up, so it's come closer to another large number, which is 6. So it's it just add 1 year, so it become a 10, and you just once it's 10, you just bring 1 year, it just become a 10, and bring 1 year, is become a 6. So eventually what happens is 0.4600. It's a 4 digit decimal floating point. Okay, but when we come to the chopping of error, the chopping of error. So when you look at the number 5 is as I said earlier, in the chopping of error will not consider that whether it's a greater or lower. So whatever the number is, they always record that the lowest point of it. So the even is 5 is only read as a 0.4599 10 power of minus 4. So that is a chopping of numbers, or is chopped at the point 5. Okay. Okay, likewise, that and example number 3. So this is a 13756.88134203. So same things. So when we consider 4-digit decimal floating point, so first we need to convert this number into NDFP form, and after that we need to look for that the 4-digit decimal floating point. So we just get that 1376. So 1376, 6 is a round off error is when is already greater than 5 and above. So you just add here, add 1 here and become a 6. Okay, and become 0.1376. Okay, 10 times 10 power of 6. But when looking at the chop numbers, okay, the chopping numbers, so it will become, okay, since even though 6 here, so it read as a 1375 because these numbers will not be counted. It's recorded as a lower and the system chopping of numbers will be counted the lowest numbers. Okay, so it becomes 0.1375 10 power of 6. Okay, is that clear, guys? Is that clear?
Yes.
Okay,
Yes.
thank you. Make sure you just put up your hand, or maybe you can leave your messages chat box if any questions. Okay. Okay, now k-digit rounding or chopping arithmetic. Okay, k-digit rounding and chopping arithmetic. Okay, so now we're going to look into that. Just now we just look at that the general forms. Okay, now when it is involved arithmetics. So arithmetic, which mean as usual we just do arithmetic operation, which is multiplication or addition, subtraction, multiplication, all right, division, square root, and so on. So okay, so we're going to look into how does it work, how we need to conclude that final answer. Okay, all right. Now, so performing computer or machine arithmetic, so x times y, so the floating point will be, first you need to change into the floating point, whatever it is, whether it's chopping or round off, you need to change that first. And for the respective x or y, then only you need to multiply. Okay, what usually the student do mistake every time in the exam was they change at the last. They round off or they do the chopping at last after the calculation. It is wrong. The computer would not do that in that way. Okay, so in computer what it will do, it will chop everything at the beginning, not at the last. Okay, please be aware that. Okay, okay, now usually how you do a maths, usually you do a maths when you at least you give that the great significant level or great decimal numbers, and then at last you round up the number to nearest 10 or nearest 100, something like that. Correct? Not? Okay, that's a general practice. It's a human do. Okay, but in computer, when you come to the computer arithmetic, you should not do that. Okay, you need to do as how the computer do the calculation. Okay, first you need to change into that whether it's a round off error or the chopping of number, you need to change it at the beginning in advance, then you do your calculation. Okay, not the other way around. Please remember, guys, these are a very common mistake. I observe all the time when the student attempt that this type of questions. Okay, now in the machine calculation, okay, so in machine calculation, usually the addition, subtraction, multiplication, and division will be represented in this form. Okay, so as you can see that here, the symbols, this is the first one is represent the addition, the second one is represent the subtraction, and the third one is represent is a multiplication, and the last one is represent the division. Okay, so always remember this form. So when you see this form, which means this operation is done by machine or computer. Always remember that. Okay. Okay. Now I give you 10 minutes break. Okay. And after that, we can come and we discuss these questions. We continue, huh? All right. Now, take a look at the example 2. All right. So given that x equal to 43.7186 and the y is given as 132.441. Okay. So they want you to just evaluate that x plus 4. Okay, this is how usually you can see the question in that exam. Okay, by practice. But remember that when you come to that machine arithmetic or computer arithmetic, so the way you will execute is in the different way. Okay, now first you need to evaluate exact value of x plus y. So exactly is how we're gonna do. What does that mean exactly? Anybody want to try? Ti Hui Boon?
Yes, doctor.
Yeah. Can you tell me what does it mean exactly? Yeah, Boon?
Just, yes. I think it's just add the x value and y value. So I get the answer is 176.1596. Hello?
Yeah, say it again. 100?
176.1596.
Okay, correct. But however, that is slightly you need to give your answers in the way of NDFP form. As I said earlier, right? Your answer should be expressed in the form of NDSFP because this is computer arithmetic exact values or true values. Okay, all right. So take a look. This is the first example questions. Okay, now we're going to evaluate x plus 1. Now, what all you need to do, you need to add these two numbers since exact value. You don't have to do anything round up of a chopping operation. So you just leave your answers as this form. So when you just add these two numbers up, so you get 0.1761596 times 10 power of 3. You have to leave your answer as in the form of NDFP. Remember, okay? So this is a computer arithmetic form. So, I mean, a calculation, you have to leave it your answers as it is. Okay. Now, next question, you need to add the two numbers up, okay, in the form of computer arithmetic. Okay. So add these two numbers up. It's not exact value, but in the form of, okay, using 4-digit rounding arithmetic. You're going to calculate 4-digit rounding arithmetic. So 4-digit rounding arithmetic means you need to chop. First, you need to convert the number, the x value into NDFE form, and as well the y value you need to change into NDFE form, and then you need to look for round up at round off numbers which is 4-digit. Okay, 4-digit. So first, what all you need to do, you look for change. You change it into that NDFP forms. Okay, is a become 0.4372 times 10 power of 2. Okay, so the 4-digit numbers, since there is a 8, so you round up to 2. Okay, is a 1 become a 2 now. So you just leave it your answer 0.4372 times 10 power of 2. And then you add up with the y value, which is you need to round up as well, the same procedure, which is change into the NDFE form. So 0.1324 times 10 power of 3. Okay, now in order to add these two numbers, remember that even though it is in the form of in the NDFE forms, so look at that, you cannot add up simply because you look at that your index. The index has to be same in order to add this number to up. So what all you need to do, you need to move this another one more decimal place in front, is make it as a 10 power of 3. So make it balanced to that the other side. Now it is easy to add this number 2. So which is 0.04372 times 10 power of 3 plus 0.1324 times 10 power of 3. Now you easily can add this number to number. So which is become 0.1761 times 10 power of 3. So this is your answer. Okay, this is based on round off number. Okay, round off number. Okay, is it clear, guys?
Yes.
Yes.
Okay, thank you, Nurul. All right, now next, look at that example 3. Okay, example 3 is a kind different, which is they want you to calculate 3-digit chopping of number. Okay, 3-digit chopping of number. So when you come to 3-digit chopping of number, so first of all, again, you have to change the given value into that NDFE form. Okay, first you have to change in the NDFE forms, and then you need to express, okay, in that 3-digit chopping number. So 3-digit chopping number, it's become 0.437 times 10 power of 2. Okay, and then again you need to change that y value in that. First you need to convert into NDFE form, and then after that you need to leave it your answer in the 3-digit chopping number form, is it become 0.132 times 10 power of 3. Okay, now you easy for you to add this to number after when you make it that the index is balanced. So which is you just move 1 point up in front, it become a 0.0437 times 10 power of 3, and it is balanced at on your right hand side. So then now easily you can add this number, which is 0.175 times 10 power of 3. Okay, now from here you can easily can identify that the error by you taking that the exact value minus that the chopping numbers. So you can see how much the difference is, the error is. Okay.
Doctor, I want to ask.
Yeah.
For part B.
Yeah.
If the final answer is 0.1, can you show the part B, please?
Part B. Okay. All right.
Okay. So if the answer 0.1761, but the answer is 2, right? The dekat belakang tu. But if the answer is 0.17615, do we have to run off again?
No, we just only change at the beginning, not at the last.
Oh, okay.
Okay, not only the beginning, not at the last. As I said, in the human calculation and the computer calculation, the difference. Okay, as I said earlier, you need to round off first, and then only you need to do a calculation. Is it clear?
Yes, clear.
Okay.
Thank you, Doctor.
All right. Now we move to that overflow and underflow error. Okay, floating error, which is happen in usually in that computer programming. So when you run a program, so there is obviously sometime when you run a program, maybe you use a different command in the C programming. So instead of use the double, maybe you use the integer. So definitely there will be floating error appear, and your calculation would not give your solution. Maybe it just back to small numbers, or maybe the system or the simulation or the iteration will be stopped. Okay, and then is a collapse. All right, so this is all because why? That because of that overflow and the underflow. So let me see that what that overflow and underflow. Okay, overflow error meaning that the attempts to express the numbers exceeding that upper limit. As I said earlier, the computer, say the IBM, usually the upper limit will be 76, 77, 76, yeah, 76, the upper limits. So which means the IBM machine usually will be 6-digit decimal point system. Usually that the index numbers is between -77 to 76. So that is a standard, is determined by the IBM. Okay, and different operating system will be the different values, like IEEE is will be a difference. Okay, and then yeah, so you need to know that the type of the computer, and then as well that the boundaries. Okay, now so overflow means the number which is you calculated, say again, it is like that the number is exceeded from that the upper limit, which is m, that determined by that the computer system. So which means what will happen? So your your system will be collapsed, and then it will be stopped. Okay, so we call it exceeding upper limit. Okay, so this causes your system or the operation will be stopped. Okay, and they give some error. Okay, now what happened that the underflow? So underflow error means the attempt to that express the numbers smaller than the limit. So when you consider small the lower limit, okay, so same thing. So when you look into that your calculation, and then the result is you getting the number which is set by that computer, they're already in that computer. So you get the lower than that. So same thing, the number will be reset to 0. Okay, this we call as a underflow error. Okay. Okay. So as I said earlier, so the IBM machine for the 6-digit decimal point usually will be in the between the range of -77 to 76. So the at most the limit, the upper limit will be the capital M is 76. Okay, the 10 power of 76, and then the lower limit will be 10 power of -77. Okay, that is a range usually in the IBM machine. Okay, but different operating system in the computer will be the different range is given. It's just an example taking from the IBM machines. Okay, so your calculation, okay, in a real system, real analysis, say in the NASA. So NASA, when is a launch a rocket, so definitely they must have that the significant error more than this, because the place which is the design the computer has to be the n must be is at greater, I mean like very large numbers, so that they will get that accurate solution. Okay, even the reason, okay, I just give you some similar scenario. Okay, I'm sure you all read about that Pathfinder, which is NASA is a few years ago they landed the Pathfinder in Mars. Okay, so what happened if the computer is not that accurate? Maybe in the overall, when we can see into that system, it is look accurate, but remember that the size of Mars, even the significant or the number of decimal places is smaller, or it's not accurate. Maybe we can use this form in the digit. So the the NASA pathfinder with not landing in the right place, maybe it's somewhere else. So as a plan, there has to be is a more accurate. So they really required is a large number size of significant places or the exponent numbers or index numbers. Okay, so that's the best examples for this kind of in order to calculate the arithmetic operations in the computer. Okay, now look at that this example. Okay, we're going to calculate that overflow and underflow error. Okay, say given that A is given 6240 and B given as 0.000429 and the C is given as 79.24. Okay, so they wanted to calculate using 4-digit rounding arithmetic, determine that following. Okay, now look at this A. So A is given A and this is multiplied by, in bracket, A multiplied by C. Okay, and the symbol here is the operation done by computer or machine. Okay, as well B, A divided by bracket A times C power of 4. Okay, so remember the symbol is as well as it is a computer operation, so it's done by the computer. Okay, now you need to explain how the result affect the computation done by under the floating point system, which is given between -9 to 9. Okay, this is your you need to identify it. Okay, you need to identify based on that given range of that the index number or the exponent value. Okay, take a look at the first example. Okay, say that the A is given and B is given and C as well. Now you need to use that the 4-digit rounding arithmetic. Okay, 4-digit rounding arithmetic. So as I said earlier, first step, what all you need to do is you take that the value A, you need to change into NDFP form. Okay, you change NDFP forms, so it become 0.6240 times 10 power of 4. And then multiply in the bracket, you need to do that, so put the bracket, so you get that A value here, okay, in the form of NDFP form, and then times with your B C value. C value is a 79.24. Again, you need to change into that NDFP form, so 0.724 times 10 power of 2. Okay, so once you're done, okay, you just simplify it and then you get that value 0.3085 times 10 power of 10. So that is your final answer. Very simple. Just follow exactly the step. That's your first step. This is your second step. And this is your third step. So 3 steps is just required to complete your solution. Always remember the steps. Okay, take a look at the second example. Okay, now before that, now we're going to identify. Now, so you need to identify whether the 10 is underflow or overflow. As we know that the range is already given, the end value, the exponent number is already given, is that between, must be between -9 to 9. Okay, now somebody. Nur Kumaira. Nur Kumaira is here? Nur Kumaira? Nur Kumaira. Nurul Ashikin? I'll take all the record
Yes.
names. Oh, Nurul, who's that? Nurul Ashikin, is it?
Ashikin.
Oh, Ashikin.
Yes.
Okay, Ashikin. Now, tell me, since we have that index now is at 10, so 0.3085 10 power of 10. So now the exponents given is 10. Okay, what does it mean based on our given range of our n value, and how are we going to determine whether it is underflow or overflow?
May I know what's the apa ni? What's the limit?
Oh, limit, I just show you just now. The limit is just given. Do you follow the slide just now? The limit is the floating point given is the minus 9 to 9. Okay, there's a range is given. Okay, all right, now how are you going to conclude the answer?
I think it is overflow error.
Okay, why?
Because the n is more than 9.
Okay, what will happen actually if it is more than that?
More than that? I don't know.
Okay, now all right, that's fine. Okay, now since we know that n value is a 10, all right, obviously we know that from the calculation we know that n value is a 10, which means this is exceeded that given upper limit, which is the maximum upper limit is a 9, so it's a greater than, I mean, more than 1. So this is reason what will happen is that the computation will be stopped automatically. So when you run your programming, so when you execute, so all of a sudden at the point when you reach a certain point, the computer or the simulation will be stopped. Okay, and this is what we call as a overflow error. Okay, overflow error. Always remember, guys. Okay. Now take a look at example number 2. So example 2 is a divided by in bracket a times c power of 4. Okay. As I said earlier, first step you need to change into NDFP form. Okay. And then since they already know that given that it's a 4-digit rounding arithmetic, so just leave it in that 4-digit rounding arithmetic form. Okay, 4-digit rounding of error, significant error, and then divided by 0.6240 times 10 power of 4 times 0.3943 is already like I already done that the calculation here. Okay, the C. So you need to change into that the is a C power of 4. So I already done that the calculation earlier. So it's become 0.3943 times 10 power of 8. Okay, and then your final answer will be 0.1743 times 10 power of minus 14. Okay, now who's this? Okay, Priscilla Raj. Priscilla.
Yes, doctor.
Okay, Priscilla, can you tell me what you can conclude based on these statements?
The index value n is lesser than the value m, so it is underflow error.
Okay, what will happen if underflow error means?
The computation will stop.
Okay, good try, but it's not. Thank you, but it's actually not a computation will be right. Is a what will happen usually that the computer or the machine memory, what it will does usually, it will be reset those given value to 0, and then it proceed again. Okay, so because the memory or the given range of that the n value is just less than what we expect, so it means it's a small numbers. Okay, when you get even smaller, so what the computer will assume it is 0 value. Okay, so then the computer automatically they set that the value as a 0. Okay, always remember this is very, very important. Okay, so I would ask this question, maybe I ask to justify for each every calculation in your exam, in assessments as well. Okay, so as you can see, obviously that n value which is minus 14, so which means is less than the given set range, which is minus 9 to 9. So since that the minus 14 is much greater than -4. So what will happen? This we call as a underflow error. Okay, we call as a underflow error. So then the computer will assume that the number is 0. Okay, the number is 0. Okay, now next, how do you lose your significant digit? So this is another questions in that arithmetic operation by using a machine. Okay, so usually, as you know, the unsatisfied law of arithmetic in floating point system, so we represent in the form x plus y, it is not equal to x in plus, which is the arithmetic operation in the computer with y. So that means that x plus y by using computer and the manual calculation done by human is always not same. Okay, it's a different, because the round off of chopping error due to k digit floating point numbers. Okay, another is the subtraction of two nearly equal numbers. Okay, so which means that the numbers almost are similar with the by decimal numbers. So it's also, and they give you that the significant digit values we lost when we just subtract two the same numbers or same almost equal numbers. And third is addition of large and small numbers. Say you take the large numbers like a 10,000, you just add up with that 0.000000005 or 6, something like that. So when you add, so since the two number is two different volumes, so it also causes that you lost your significant digit. Okay, and at last, the greater number of arithmetic computation due to intricate formula. That means the more complicated or more sophisticated formula or the expression. So this is the causes where you lost your significant digit in that computer calculations. Okay, now look at that example 4. Okay, we discuss quickly on this. All right, so given that the x value is at 10,000, and given the one approximation function, which is function fx, given square root of x plus 1 minus square root of x, and they wanted to using 6-digit rounding arithmetics. And second question, x plus y, and given x and y value, using you need to use that 4-digit chopping arithmetic. And then the question C, they given a function, a cubic function, and the x value given is 2.18. Okay, and then they want you to use that 3-digit chopping arithmetic. Okay, now we execute the first one. You look at that value. So now you attempting to get that the solution. All right, for that the using computer arithmetic or machine arithmetic. So we just substitute those value, all right, into the function. Okay, plus 1. Okay, remember that, as I said earlier, first you need to change into in the form of NDFE form. Then you need to execute your solution. Okay. All right. So and then you get the answers. You 0.500000 times 10 power of minus 2. Okay, now you're going to comparing your answer with that exact solution. Okay, and you can obviously see the difference between that exact solution and then the computer arithmetic, and then you can see that how they lose their significant digit in these forms. Okay, that's our first example. All right, second one, similar. All right, so you're going to use that the x plus y using that computer arithmetic. Okay, and the value of x already given. Okay, yeah, it's supposed to be a. Oh no, x. X, right. Okay, x and y. So x is already given. Change into the NDF forms, and then you get the result. Okay, and then you're comparing with that exact solution. Okay, So in the human way, and you can see that the differences between these two. Okay, so you can obviously see that the differences between that, what happens by using that the exact solution with that the computer arithmetic solution. Okay, now look at that the example 3. Likewise, same things. You need to attempt using the computer arithmetic way. So you substitute those value, as I said earlier, change it to the NDF forms, and then substitute accordingly, and then you calculate, and then you look at your final answer is 0.579 times 10 power of 2. Okay, and then you compare with the solution with that your exact solution. All right, and see the differences, how much the difference is. Okay, you're losing a significant digit. Okay, so this is the difference between that computer arithmetic as well as the exact solutions. Okay, all right, so I think this is a pretty easy, straightforward. Okay, I already give that the sufficient example in order to make your own practice. Okay, and if you still find any difficulties, okay, you let me know during the tutorial times, and I will teach you how to do it. Okay, all right, for the practice, all right, I want you to attempt this, your own practice. You can use as the example the what I showed you earlier. Okay, use this example, and then you find out all that the figure according to that given instruction, which is for the exact solution, and then using 3-digit rounding arithmetic, and then 4-digit chopping arithmetic, and then you need to compute that the relative absolute true error and absolute approximate error respectively. So you need to look for that every solution, and then at last you need to look for that absolute true error as well the absolute approximate error. Okay, this is your homework. Okay, you practice and let me know if you anything. You check with your friends your answers, your solution, whether it's you get the correct answer, the same or different answer. If a different answer, and then you look for me. Okay. Okay, guys. Any question?